This is FRM Part 2, Book 2, Credit Risk Measurement and Management, and the chapter on portfolio credit risk. Of course, what we're focusing on in this chapter is credit risk, not interest rate risk. And of course, we're going to eliminate those bonds issued by the Treasury Department here in the United States, and we're going to focus on risky credits. Now, when I first looked at this chapter, I was thinking that we're going to talk about the entire universe of bonds, but for some reason, at the beginning of the chapter, they mention corporate bonds, some off-balance sheet exposures, commercial paper, and credit derivatives. So I thought there was something interesting about those, and I don't think there really is in the chapter, although there's some interesting examples that are discussed in the chapter. So let's go ahead and look at these learning objectives. Now, the one interesting part of here is that there are two define and calculates. We're going to have to look at default correlations and credit value at risk. And I'll show you how to calculate those things. And they're relatively simple. We'll look at some drawbacks because we've had this conversation before that correlations tell us something about a relationship, but not everything that we need to know. We'll go ahead and have a good conversation on credit value at risk, and then we'll talk about some granularity at the end of the slide deck. So let's go ahead and start with an introduction with this concept of default correlation. Now, of course, correlation means exactly what it's always meant to us. It's a measure of the direction and magnitude of a relationship between two random variables. So default correlation is going to be exactly what you think the name suggests. It's going to be a measure of the relationship between the default on two or more credits inside of the portfolio. And there are two normal distribution pictures there at the bottom of the slide. We're interested in the probability of default. Remember that we're always concerned about that left tail. So what we want to do is we want to look at the correlation between the returns on credit A and the returns on credit B. In this case, we just have A sub I and A sub J. And the other interesting thing about this chapter is that we're concerned about these defaults occurring around the same time, maybe not on the exact same day, but certainly within some relatively short time period. Now look at that second block point that I have written there. Default correlation, important risk management tool when analyzing the benefits of credit risk diversification. We're going to have a slide later on that illustrates some of the benefits and when they occur and when they may not occur. All right, the chapter begins with a discussion, relatively simple discussion, on an investment in the credits of two firms. And so if you look at the slide at the bottom, we have Firm 1 and Firm 2, and look at the timeline as it goes across. And so notice I have the word solvent next to both of those. So as we go through time, both of these firms are solvent, so the bonds are not defaulting. And as we go through time, notice the two lightning bolts hit at the same time period, relatively the same time period. And we identify that thing as a joint default. So let's go back up to the circle points. We have positions in the two firms. The probability of default for each firm is defined as pi sub 1 and pi sub 2. And that time horizon is time period tau. And then the joint probability of default, and I have this in red bold, is pi sub 1, 2. So that's where the two lightning bolts hit at the same time. Now, of course, we need to go back to our understanding of all the distributions that we've had discussions about in previous slide decks. And if we have the case, which we do now, of either a default or a no default, then we have just two outcomes. And so this scenario lends itself to using the Bernoulli distribution, which, if you remember, is the simplest of all discrete distributions. And so with an investment in 2 credits, we have 4 possible outcomes, and I have a table here. And so notice down the left-hand column, we have the outcomes in which neither firm defaults at the top, or both firms default at the bottom, and then 1 or 2 defaults somewhere in the middle. So we have X1 and X2, those are the individual credits. And then we have X1, X2, and those are the combination of the two, along with their probabilities on the far right column. So note that 1 is equal to default and 0 is equal to no default. And then the chapter gives you a pretty good definition of the default correlation. So here we have our first stab at some mathematics, and that default correlation is defined as all correlations are defined. There's the covariance in the numerator, and then in the denominator, the product of the 2 standard deviations. Now, what the chapter then does for you is go ahead and defines a joint default probability. That's the pi sub 1, 2. And I bolded the default correlation in there. And as I was first reading the chapter, I was reminded of circularity. And that kind of posed an interesting problem for me as I was reading this the first time. Notice that pi 1, 2 and rho 1, 2 are both on the left-hand side of the equation and on the right-hand side of the other equation. So there's some circularity here. But then as I read the chapter, I realized, and the chapter actually does a good job of defining the joint default probability as a primitive parameter. And so it's primitive meaning that it's critical in determining some other parameters, which in this case is the default correlation. Let me go ahead and show you what I mean by that. Let's take a look at an example. Let's suppose we have a position in 2 credits. We've got a AAA rated bond and a BBB rated bond. And so our probability of default, there's that pi 1 and pi 2, is 0.001 and 0.004. That should make sense, right? The AAA rated bond has almost no chance of default. BBB rated bond also has almost no chance of default, but it's about 4 times the size. And then this is what I was talking about earlier about this primitive parameter. We're going to assume that we can either estimate or calculate, or some way we can come up with this joint probability of default. And there it is, 0.00018. So we'll use those inputs to compute the default correlation. So this takes care of that learning objective of defining and computing the default correlation. And so if you do the math there, you get 8.82%. Now, I also wanted to swing you back to example 7.1 from the chapter to illustrate one of the important parts of the early part of the chapter. We've got 2 credits. We have probability of defaults, and this is taken right from the chapter, by the way. So probability of default is 2 zeros and a 25, and the second one is 1 0 and a 125. Now, here's the important part of this. If the defaults are not correlated, so let me go back to down here at the bottom. If those defaults are not correlated, the input variable in the red is 0, and all we're left with is the product of those 2 individual default probabilities. So let me swing back here. If you multiply the 25 by the 125 and all the zeros in there, so if the defaults are uncorrelated, then that joint default probability is, what is that? 4 zeros and a 31. Think how low that joint default probability is where the 2 lightning bolts hit each other. However, if those defaults are positively correlated, let's just throw in a number there that your chapter does, 0.05, then the joint probability is just 3 zeros and then about a 31. So it's about 10 times as great. And so I put this here on the slide to illustrate the value of those that assumption that the defaults are uncorrelated. If they're uncorrelated, then we have we have almost no probability of those lightning bolts hitting each other. But as we get into positive correlations like 0.02 and 0.05 and 0.1 and 0.2, I think the chapter gives an example of a 20%. Then those joint probabilities increase. Okay, that should make perfect sense. Now, what did I say just a few slides ago? That correlation provides us with lots of information, but it's not perfect and it's not complete information. And so one of those learning objectives asks us to identify the drawbacks. So what did we do in that previous slide? We had 2 credits, right? But what if we have 20 credits or 200 credits or 2,000 credits? Then in order to compute those correlations, we need tons and tons and tons of pairwise inputs so that we can calculate those. And I'm guessing you guys remember that formula is always n times n minus 1. So whatever, what did I say, 200 or 2,000, say 200 times 199, whatever that number is, I mean, you can think of a gigantic Excel spreadsheet. So the chapter calls that the curse of dimensionality, meaning that there's lots and lots of inputs out there. And it'd be one thing if we could just pick up the Wall Street Journal and find all those inputs. But remember, these are not easily observed, and sometimes they're difficult to estimate. Now, the other issue is that actual default is a relatively rare event, which means that since those default correlations are going to be very small in magnitude, they're probably difficult to measure and difficult to estimate. And then the third drawback is probably why I said this to you just a few moments ago, that the beginning of the chapter mentions derivatives and some other kinds of contingent securities. And so the models, this correlation credit model that we're talking about here, probably doesn't lend itself to the evaluation of credit risk in those types of securities. You know, much like duration doesn't give us a complete measure of interest rate risk for a callable bond, we need to worry about convexity and a couple of other things to have that complete description of risk. So I would know those 3 drawbacks right there. All right, moving on to credit value at risk. We can define this as the credit loss minus the expected loss of the portfolio. And so what we're tempted to do is say, all right, credit value at risk is identical to all the other value at risks that we described in previous slide decks that mostly related, most of our conversations were in the equity market. But what I will say, and the chapter does a pretty good job of emphasizing this, is that the credit value at risk is similar, but it's not identical. So let's remember this definition is the credit loss minus the expected loss of the portfolio. And if you remember that learning objective, we're going to have to do some calculations, and I show that to you in a few slides here in a second. But let's go ahead and look at that second block point here. This is important. The default correlation is going to affect the volatility and the extreme quantiles of loss rather than that expected loss. And you'll see that here in just a second. And so it's important to remember that default correlation will impact the credit value at risk of a portfolio. And so I want you to, here, let me go back to this very first one. How far back was that? Yeah, that was way back here. And so remember, when we're looking at this value at risk, we're always concerned about the left tail. And so here are just 2 pictures of possible left tails with normal distributions. And so our focus is going to be on the credit value at risk. And here, let me swing back here. That's going to be the credit loss minus the expected loss of the portfolio. Now let's look at what happens if default correlations are at some extreme number. So suppose that its default correlation of the portfolio is equal to 1. Well, what that means then that if we have even if we have 10 credits in the portfolio and the default correlation between and among them is exactly 1, well, then that portfolio looks an awful lot like it just has 1 credit inside of it. And so, of course, there will be no diversification benefits. But on the other hand, if the default correlation is equal to 0, then of course we might have significant credit diversification that might be achieved, and we'll see that here in just a few slides. Now, what the chapter does is take you through a couple of examples. I'm going to do 3 of them here. Your textbook does a bunch of them. It has a big table that fills up almost 1 page. So let's look at a portfolio that has $100 million in value, and we only have 1 issue in there, 1 credit. So the default correlation is 1. Let's assume a default probability of 2%, and then we'll have a confidence level of 95%. Now, before we do the math, you ought to scratch your head and start thinking along the following lines. You should say something like, all right, Jim, wait a minute. We have a default probability of 2%. That means that we have a 98% probability that we're not going to default and a confidence level of only 95%. So let's scratch our heads and see what kind of a result we get. And so, this is a little interesting here. So this is what happens. The entire portfolio will act as if it is a single credit. So the expected loss is going to be the 2% times the $100 million portfolio value. That gives us $2 million. And so the credit value at risk is going to be the credit loss minus the expected loss. And remember, we're doing this at the quantile. So we're going to take 0 minus the 2 million gives us a credit value at risk of a minus 2 million. This is like a gain. So you can go ahead and calculate it, but it really is not too helpful. And that's because of the difference between the 95 and the 2%, and the fact that we just have 1 credit inside of the portfolio. So let's go ahead and add a bunch of other credits to the portfolio. Let's suppose that we're up to 50. We still maintain that 2% and 95% confidence level, but now out of the 50, we have 3 defaults. So let's go ahead and compute the credit value at risk. So what happens now is that when an N of 50, let's go ahead and take that 50 into the 100 million, and that gives us each position of $2 million. And so that expected loss is going to be 2% of the 100 million, which is still the $2 million. Now, if there are 3 defaults, that gets us up to 6 million. So you take the difference of 6 million and the 2 million, that gets us a credit value at risk of $4 million. So back here, let me go back to that first example. We have a minus 2 million. That doesn't make a whole lot of sense. Now we've got 4 million, and we can work with this number when we have 50 credits. Now let's quickly go through an extreme example. Let's suppose that we're up to 1,000 credits. We've got some big mutual fund or some big pension fund, and that default correlation is 0 now. And we've got same 2%, same 95%, but the number of defaults rises to 28. So that credit loss now becomes only the 28 times the $100,000 per individual credit, which is the 2.8 million. Subtract that 2 million of expected loss, and now that credit value at risk is down to $800,000. And so this begins to address that one learning objective about the granularity. So we started with 1, then we went to 50, and then we could have gone to 100 or 500. Now we're up to 1,000. I guess we could go to 2,000 or 5,000. So here's a little summary table. So as we increase the number of credits, what happens to the credit value at risk? One thing is pretty clear. As the portfolio becomes more and more granular, the credit value at risk decreases for a given default probability. However, what's really interesting in this is that when for a very large number of credits, like that 1,000 that we had there, the probability converges to about 100% that the credit loss is going to be equal to the expected loss, and that credit value at risk is going to be equal to 0. So look at that second block point here. It is harder to reduce the value at risk by making the portfolio more granular if the default probability is low. In other words, that low default probability is really not going to impact the credit value at risk as much when the portfolio becomes more granular. Now, implicit, let me go back here, implicit in all this stuff. Here we had default correlations of 1, then we had default correlation of 0, default correlation of 0. So we were limited to, let me go back to this slide here, inside of this little box here. So we were limited to the 1.0 and the 0. Well, of course, we're going to have default let me go all the way back here. Of course, we're going to have default correlations that are somewhere between 0 and 1. So the question then becomes, how do we deal with default correlations that are 0.2 or 0.5 or 0.7? And well, we don't have to look any further than our previous discussions on single factor models. So we're going to use this single factor model so that we can account for default correlations that are somewhere between 0 and 1. What that means is that we're going to have a correlation. The text calls it a beta correlation. Now, I'm going to point something out here in just a second. We need to be careful. And then some idiosyncratic shock variable. There's the epsilon sub I. All right, so look at the bottom in the blue box there. The firm's individual asset return is given by, so we're going to use the notation A sub I, individual asset return, is equal to, now there's the beta correlation times some market variable. And I want to make sure that you don't confuse this with the equity beta, which can be between 0 and 2 or whatever number it is. This is a correlation, so it's going to be between 0 and 1. Don't confuse it with the equity beta that we talked about before. So the return on an individual asset is going to be the sensitivity with the market and then the sensitivity inside of that particular corporation or issuer. So let's take just the extreme example. Suppose that our asset is the S&P 500 index. So that beta correlation is going to be 1. So the return on the S&P 500 index is going to be equal to 1 times, let's suppose the market goes up by 10%. So that's 1 times 10%. And then the plus sign, we're going to add that standard deviation over there. We're going to take 1 minus 1 squared is just 1. So that term to the right-hand side of the plus sign, that goes away. And that should make perfect sense. But what happens then, this is why the single factor model is so cool, is that let's suppose that we have a correlation of 0.5. So the return on our particular asset is going to be half of, what did I say that market portfolio return was? Let's just say 10%. So half of 10% plus something that's going inside of that firm. So what is 1 minus a half? That's a half. What's the square root of a half? What is that, about 0.7? So we're going to take 0.7 times whatever that idiosyncratic shock is. You know, maybe it's a default, maybe it's the death of the CEO, or maybe it's some other kind of a shock. And then we're going to evaluate that individual asset return based on market forces and idiosyncratic forces. So you see the advantage of this single factor model. What we can do is we can allow that correlation to float between 0 and 1. And then here are some summary equations and definitions for the single factor model. And the important part here is the very bottom, and that's why I bolded it. So the covariance between asset A and asset A sub I and A sub J, and all the way equals, forget about all that stuff in the middle, although you could probably work through it. Look at the far right, bottom far right is going to be the product of the two correlation coefficients. Now, once a particular value of that market factor is realized, then those asset returns and the default risks are going to be independent of one another. And so the conclusion here is that those firms' returns, let me go back to this thing here, the returns right there are correlated only with their relationship to the market factor. So these default probabilities then are going to be conditional on market movements. So all the stuff that we learned back in the single factor model and the single index market model, and then the Ross multi-factor models applies here. We're asking the question, what happens to credit risk when there are events in the entire market? Now, these joint defaults, those lightning bolts, this is a big problem for portfolio credit risk managers. We need to worry about the company's unique scenario, which we just described, but as emphasized in this previous slide, we also need to worry about the state of the economy and maybe some industry factor that has a unique influence on the individual asset returns that may or may not be captured by the state of the economy. And so where are we in our conversation here? We know that correlation is, what did we describe that as previously? It's some scalar measure of dependence. It gives us a lot of information, but it doesn't tell us everything. Which is why then the end of their chapter starts talking about copulas. And remember, those copulas, they join marginal distributions to form joint distributions that tell us something about that left-hand tail. And they tell us something about that left-hand tail, especially when variances are high. And so we're going to have to go back to our discussion on copulas so that we can simulate these joint defaults. So let me just quickly remind you, let's identify a copula function. There it is, which then leads us into the steps in computing that credit value at risk. So we're going to specify the copula function that we have before, simulate those default times, and then apply those default times to get market values and P&Ls for each possible scenario. So think of, some kind of an Excel spreadsheet where you can do profit and loss depending on whether market factors are up or down, and then you can get those portfolio distribution statistics, which will allow us then to estimate that credit value at risk. And I think that takes us through those learning objectives.